Hey everybody, this is Phil. I just wanted to show you another demo of Fil-C. This time I want to demo a new feature I just implemented, which is memory safe mmap, which allows for memory safe shared memory IPC as well as memory safe memory mapped files. I'll just show you the shared memory IPC here with the simple program that I wrote, which allocates some memory with mmap and then forks. And then inside the child, what it'll do is it will copy this message into a buffer. This buffer is stored in this shared struct that's allocated in that shared memory we allocated. After copying the message and doing a store fence, it will just set a flag telling the parent that the message is there. Afterwards, it unmaps the memory. And in the parent, we're going to wait for the flag to be set, and once the flag is set, we're going to print the buffer out. So let's see what it looks like to compile this program with Fil-C. It's compiled, no big deal, and then we can run it, and you can see that we allocate the memory, which is this printf here. Then we fork. The parent then starts waiting for the child to set the flag. And then the child goes ahead and you can see it copies the message. It's setting the flag, and then the parent gets the message, prints it out, and says memory safe shared memory IPC wow. And that's that message right here. Now, what do I mean by this being memory safe? It's memory safe in the sense that there's no way that you can use this API to violate the memory safety guarantees of Fil-C either in the child or in the parent. You're only gonna be able to write within bounds of that allocated memory. Because shared memory, you're only going to be able to store raw integer data into it. And even if you unmap it, there's no way that this could corrupt the process's memory in such a way that, for example, there's some use after free where you still have a dangling pointer to the memory, and then you use it even though the memory is free and end up overwriting some other objects. So let me show you some examples of what if you get this wrong, right? So for example, if I move the mmap call in the child up to before the copy, let's recompile and run again, you can see that now the child is trying to copy the message into the buffer. But now it can't because it needs the span to be integers, but that span is now free and contains the free type within it. So that doesn't work. And now the parent is waiting forever for the child to set the flag, and it never sets the flag. So let's undo that. What if the parent does something similar? For example, what if the parent unmaps the memory just before trying to print the message? So let's compile, run again. And now you can see the child is fine, but when the parent tries to print the memory, it gets a similar error saying that the memory is now free. What about other stuff that you can do? What if we instead tried to pass a pointer? So let's say this is just a string pointer, and instead of stir copying, we're going to just point that pointer at the message. So this would be wrong because you're not guaranteed that the pointer in the child process and the pointer in the parent process will point to the same thing in all cases. In this case, in normal C, you might kind of get away with it because this is a string that's in global memory, so hopefully it's the same pointer in both. But Fil-C is going to disallow this. Let's just make sure that this program compiles. So we've now gotten it so that it will compile, and here's what will happen. So as the child is trying to set that pointer on line 23, there's line 23, you get an error saying that you can't access that memory as a pointer because it's integer memory. And again, the parent in this case is stuck waiting forever for that message to come through, and it never comes through because the child crashed. So let's revert that and go back to having a buffer. But what if you try to go out of bounds of the memory? So I don't know. Let's do that by having a loop that stircats the buffer a bunch of times. So let's see what happens then. So in this case, what happens is the subsequent stircat overwrites the flag, which means that the parent thinks that everything is fine and ends up printing multiple of these messages. But eventually, what happens is that the child crashes because it goes out of bounds of the buffer. And you can see that error happening here. So it's trying to print to a pointer that is now above the bounds of this allocation. So that doesn't work. Let's revert that. So we're back to a working program here. Okay, there we go. So that's Fil-C doing memory safe shared memory. But let me also show you how this code is actually implemented. So I'll just walk you through everything that I had to do to implement it. So first of all, I added in stdfil zsys, mmap, and munmap calls. So this is the low-level syscall API that my libc is going to use. And I had to modify muscle so that in its mmap implementation, instead of doing what it normally does, which is to make a direct Linux syscall, it's calling zsys mmap instead. In order to support this, I also had to edit the script that generates forwarders for when a Fil-C function is actually implemented inside libpslow. So you can see I added these two lines here, adding the signatures of zsys mmap and zsys munmap. What this does is it causes the following code to be generated. In here, it generates a native thunk for zsys mmap. And this thunk basically quacks according to the internal Fil-C ABI, but it's normal C code. It's just following the Fil-C internal ABI. And it's making sure that that all of the arguments that are being passed are translated into the way that normal C calling convention would work. And it knows all their types, so it knows what to do with them. It also makes sure that all the pointers that are passed through that API are tracked appropriately for garbage collection. And then the actual function is exposed through this getter that returns a pointer to the function. Because in Fil-C, every global symbol is resolved by calling one of these getters that gives you a Fil-C pointer to that symbol, so that we know that we're pointing, in this case, to a global special function. So now let's look at the Fil-C runtime code for this. So this is this is the function that's going to be called. And what this does, actually, before I show you this, I had to add one more special thing to the runtime data structures. So what we're going to do to implement mmap, what we do to implement mmap, is that the mmapped memory actually gets a full Fil-C capability. Fil-C capabilities are represented by these GC allocated Fil-C objects. That these are immutable objects for the most part. They track the lower bound, upper bound, the flags, and then the word types. So the type of every 16-byte word inside of that memory, every 128-bit word inside of that memory gets a 1-byte word type. Because we're doing a shared memory allocation, these word types are going to be int, so that we can't pass pointers across the shared memory. Normally, when a Fil-C object is allocated, after these word types, the actual payload of the object is allocated. But for mmap, we're going to do something different, which is that the lower and upper bounds of the Fil-C object is going to point to that mmapped memory. So there's going to be both a GC allocated Fil-C object and the actual mmap. And just to prevent you from passing that object to free, I added this extra object flag to indicate that it's an mmap pointer. That also helps with debugging, so that when you trap on accessing one of these incorrectly, you know that you're trapping on accessing mmapped memory. So the actual implementation of mmap, first of all, we're translating muscle's notions of all of these flags to the system concept of those flags. So the prot flag, muscle uses 1 for read, 2 for write, so we translate that. We only support shared, private, and anon flags, and we translate those appropriately as well. And then the actual mmap implementation, currently I don't support fixed mmaps, so the address has to be null. Fixed mmaps are disallowed just by virtue of the fact that I don't support the fixed flag. Then I convert the prot parameter, I convert the flags parameter. The OS probably does this check too for me anyway, but I do it just to be safe, that you're not passing both shared and private at the same time, and that you're passing at least one of shared and private. And then in here I do a Fil-C exit. This tells the garbage collector that I'm about to run something that's native and that might block, and that all my pointers to Fil-C memory are accounted for, which they are thanks to that forwarding thing that I showed you. This is already accounting for all the pointers for me, so I can safely exit. This means that if mmap takes its sweet time, then the garbage collector can run and handshake this thread if it's blocked in the mmap. I do that for all system calls. Once that returns, I enter back in. If there's an error, I call back into musl to set the error now and return the error result. This is just I'm forging an invalid pointer that's a pointer to -1. So this is an invalid pointer will have a null object, so you can't access it. Basically, mmap uses -1 as a special pointer value to indicate error, so that's for that purpose. So you won't be able to access this pointer because it's an invalid pointer. Any access will trap, but you'll be able to compare it to -1. And then what I do is I say that if it's a private mmap and it's anonymous and there's no offset and FD is -1, then I will initialize the Fil-C object to have the unset type, which basically allows you to use that mmap to store pointers and any kind of types, just as you would if you had called malloc. But if any of those things are not true, then I'm going to initialize it to int. And then I call this function that I have in the runtime, Fil-C allocate with existing data, which basically allocates a Fil-C object to represent the capability of having this pointer in length. And I pass the special flag that I introduced, the mmap flag, and the initial word type. And then that's it. After that, I'm done. This assertion obviously always holds, but I'm a belt and suspenders kind of guy when I write runtime code, so I assert everything. By the way, these PAS asserts are never compiled out. They're in production as well. And then on the munmap side, this is actually kind of interesting. First of all, I call the object for deallocate helper, which my free implementation also uses. So this checks that you're going to deallocate a non-null pointer, and that the pointer points to the lower bound of its capability. And by the way, in the what I also did was I said that the normal Fil-C free call now checks that you can't free an mmap. So if you try to free an mmap, it won't let you, just as an additional safety guarantee. So let's go back to munmap here. And then currently, I only support munmapping exactly all of your mmap allocation. I could add support for munmapping partially in the future, but for now, I just keep it simple. And I assert that you're munmapping something that you mmapped. Then I call Fil-C free YOLO, which is the underlying freeing implementation for object capabilities. After this call returns, any subsequent attempt to use that object, or any attempt to use any pointer that points at something with that object as its capability will now trap. But we want to make sure there's no race condition where the munmap call succeeds, but meanwhile some thread is halfway through doing the check. It's already checked that it can access the object, but hasn't accessed it yet. So it hasn't seen that we freed it and then accesses it. The way we prevent that race is we do a soft handshake before munmapping. The soft handshake with this no-op callback asks the runtime to have every thread just check in with us to make sure that it's not in the middle of doing a Fil-C memory access. It's not in between a check, and the actual access. Then we do the munmap. At that point, it's safe. Note that normally freeing an object does not require the soft handshake, because normally freeing an object in Fil-C means that the object is just cleaned up by the garbage collector. Here, the capability object will still be cleaned up by the garbage collector, but we're freeing the payload manually, calling munmap, hence the soft handshake is necessary. And then we do that. We exit before soft handshaking and munmapping, and then we enter back in, and we're done. So that's basically the complete implementation of mmap and munmap in Fil-C. It's totally memory safe, safe to use for memory mapping files, using mmap just to allocate memory if you want to have more control over how it's allocated, and safe to use for shared memory IPC, just like my example showed. All right, thanks for watching my demo.